talk will be by Paolo Pistone. And that will also be a recorded talk, which Alejandro will start now. What's decidable about atomic polymorphism? Paolo Pistone.
Hi everyone, this is Paolo Pistone from the University of Bologna, and this talk is going to be about type-related properties for the polymorphic lambda calculus or system F. This talk is joint work with Luca Tranchini from the University of Tübingen. Okay, as everyone knows, system F is the extension of the simplified lambda calculus with quantification over types. This quantification over types comes with introduction and elimination rules, which can be seen as typing rules for a lambda calculus extended with operations corresponding to type abstraction and type application. Just to give you like an idea, a guess of the huge expressive power of system F, it's worth to recall that the numerical functions that can be typed in system F coincide with those which are provably total in second order Peano arithmetics. Okay, we talked about type-related properties. Those properties that we're going to consider are, first of all, type inhabitation. So the property given a type to know whether there exists a term of that type. So in logical term, this is just the usual provability property. Type checking is the property by which a term can be given a certain type in a certain context. Typability is the property by which a term can be given a type, whatever, in a given context. And finally, contextual equivalence is the property of knowing whether two terms of a given type can be separated by means of some context. So what these four properties all have in common when we consider system F is that they are all undecidable. This is one reason why people have started different ways to restrict the polymorphic lambda calculus in such a way to make at least some of these properties computable. Probably the most well-known restriction of system F is the so-called system of ML-polymorphism. This is obtained by essentially restricting the shape of the types which can occur in type judgments. In particular, one requires those types to be of rank 1. This essentially means that one is that we do not want universally quantified types to occur to the left of an implication. So in particular, for example, the type for all x implies x is okay, but the type for all x implies x implies something is already rejected. Okay, so this restriction comes with a big shrinking of the expressive power. In fact, the numerical functions that can be typed by ML polymorphisms are a subset of the set of the Kalmar elementary functions. So in fact, which means that not even all primitive recursive functions can be typed in this fragment. However, the main reason for the huge success that this system has had is the fact that by these restrictions, type checking and typability become decidable. And this is why ML polymorphism has had a lot of application, especially in several well-known functional programming languages. Another family of restriction that has been studied a lot is that which arises from predicative restriction. In this case, one is no more trying to restrict the shape of all the types that occur in a type judgment, but instead one is restricting the types that can occur in type instantiation as type applications. In particular, the system F1, one requires the type applications to be based on types which are quantifier free. But one can actually consider a full hierarchy of more and more complex predicative fragments. But if we now stick to the system F1 with the restriction you see here, we see that also this restriction comes with a shrinking of the expressive power. In particular, the numerical functions that can be typed in the system F1 coincide with the super exponential function. So a bit more than those which are representable by ML polymorphism, but still a lot less than the primitive recursive functions, and of course a lot less than those which are representable in full system F. Well, in spite of this restriction, in fact, it is well known that already the system F1 does not have decidable type checking nor a decidable typability. So a natural question here is what's happening between ML polymorphism and predicative polymorphism so that type checking, to make type checking from decidable to become undecidable. And in fact, we think that a good way to approach, to try to understand, to try to have some insight of this kind of question comes by considering yet another predicative fragment of system F, which is the system FAT of atomic polymorphism. The system is defined similarly to F1, but instead of requiring type applications to be just quantifier free, one requires them to be atomic, that is to be just type variables. So this even stronger restriction comes with a stronger shrinking of the expressive power. In particular, now the representable function, numerical functions, coincide with those which are typable with the simplified lambda-calculus, that is the extended polynomials. Well, in spite of this, like very apparently very weak power, in fact, we will see that the system FAT can actually be seen as a sort of type refinement system for the simplified lambda-calculus. Well, the system has attracted some attention in recent years due to the fact that one can define an embedding of propositional intuitionistic logic inside this system. It is well known that propositional intuitionistic logic can be embedded inside system F by what is usually called the impredicative embedding of conjunction, disjunction, etc. But in fact, this embedding can be tweaked in such a way that, well, the interpretation of type remains the same, but the interpretation of proofs or programs is now fully predicative. Well, in spite of the attention that this recent construction have received, and that have led some authors also to propose system FAT as a convenient sort of meta language to talk about propositional intuitionistic logic, there's not much that is known concerning the decidability of type-related properties of system FAT. And in fact, this is like the main focus of our attention in the paper. And also our goal is, and hope was that by trying to understand what is decidable about atomic polymorphism, this could give us some insights, some intuitions at why certain properties, and actually all the type-related properties we mentioned before, are undecidable in the case of system F. So this is a general picture of what is known from the literature about decidability and undecidability of type-related properties for system F and some of its fragments. And in the paper, we basically answer to most of the gaps. We closed most of the gaps from this table. In particular, we show the decidability that certain properties which are undecidable already for the systems for predicative polymorphism like F1 are decidable in system FAT, like in particular the type checking and typability properties. And this will, as we'll see, will provide us with some insight as to where the problem lies, what makes type checking undecidable already in the case of system F1. On the other hand, we will see that some properties, like for instance type inhabitation, are undecidable already in system FAT. And this will suggest actually that here undecidability is not really related to the expressive power, to the predicativity and predicativity divide, but really somehow related to quantification in general. Well, so now let's try to have a look in some more detail to some of these properties. And let us start from type inhabitation. So we just mentioned that type inhabitation is undecidable in system FAT. In fact, this fact holds was already essentially implicit in Sørensen and Urzichin's book, where in fact an argument for the undecidability of type inhabitation in full system F is provided by encoding some undecidable fragment of first order logic inside system F. But by closely inspecting their proof, one can see that actually they're embedding as image system FAT. So one does not need full system F for the embedding. In fact, their argument actually works. Proof already establishes the undecidability of type inhabitation in system FAT. But it's actually a bit more than that, because one can not only encode some first order fragment inside system FAT, one can do one can actually encode system FAT itself inside some first order system. In particular, it suffices to consider first order intuitionistic logic in a language with a unique monadic predicate, P of X, because then one can actually easily embed the language of FAT by translating a type variable X like SD8 on P of X and replacing systematically second order quantification by first order quantification. And actually, if now one restricts our first order language so that the only connectives are now implication and universal first order quantification, one can actually see that the translation that you see here is actually a bijection. And in fact, it's not difficult to convince oneself that FAT coincides with this, basically with the implication and quantification fragment of first order intuitionistic logic with one monadic predicate. So in particular, the undecidability of type inhabitation in system FAT implies the undecidability of probability in this very weak fragment of first order monadic logic. And apparently this result was not known from the literature, where in fact undecidability had been proved for the fragment with an arbitrary number of monadic predicates, or for a language with one monadic predicate, but containing also this junction as a connector. Okay, we now pass to type checking. So we already mentioned the fact, the very well-known fact, that type checking and typability are decidable in ML. Well, this is proved with the much celebrated algorithm of Milner-Damas, which is based on first order unification. So the idea is that the problem of typing a lambda term can be reduced to a system of first order equations. For example, in this case, you see the application of the variable y to x leads to an equation between the types of the two variables. We also mentioned that when we step to F1, type checking and typability both become undecidable. And the proof of this fact is usually based on a reduction to type checking of some variant of second order unification, which is an undecidable problem. To have a grasp of why one needs second order unification, it suffices to observe that in systems like F1, one can type terms which contain self-application, like the one you see here. And if we try to type this term in a first order way, then we would end up with this with a cyclic equation, which can certainly not be solvable by first order unification. Instead, if we now think that theta is a second order type, so it's a universally quantified type, and that any occurrence of x comes with its own type application, then we can actually reformulate our cyclic equation as a second order one, because theta is now a functional symbol, and this kind of equations can be solved in a simple way. However, the general problem of solving systems of second order equations, in particular system of second order equations, including cyclic equations, is undecidable. Now, what can we say about system FAT? So we already said that we show that type checking and as a consequence typability are decidable in system FAT, but how can we overcome this kind of difficulties? Well, the crucial remark here is the fact that, as we already mentioned before, one can see system FAT as a sort of type refinement system for the simplified lambda calculus. More precisely, this means that for any type derivation in system FAT, we can deduce a type derivation of the simplified lambda calculus associated with it, basically just by deleting all second order information. And this has the consequence that if ever some cyclic equation were found when trying to type check a term from in system FAT, then by this embedding into the simplified lambda calculus, we would obtain a cyclic equation for a type checking problem in the simplified lambda calculus. And since the latter is solved by first order unification, we know that if a cyclic equation occurs, then the problem has no solution. So this means that a term which type checks in system FAT cannot produce cyclic equations. And this leads to basically devise an algorithm for type checking, which works in two steps. And the first step, it checks. We consider the simplified lambda calculus type checking problem, which is associated with it. So if this problem fails, okay, because some cyclic equation is found, then we reject the whole type checking problem because the solution cannot exist. Instead, if the first order, so the simplified lambda calculus problem is solved, well, this does not mean that we have solved our original type checking problem, but at this point, we can apply basically some form of acyclic second order unification, that is second order unification problem when we know that no cyclic equation can occur during the computation. And now this problem is in fact decidable. And what we do in the paper is that we show that some variant, an appropriate variant of this acyclic second order unification problem can be used to properly type check terms of system FAT, once we already know that no cyclic equation can occur. Okay, so the last thing I want to talk about is contextual equivalence. So as everyone knows, in System F, there is a standard notion of equivalence, which is beta equivalence, and this equivalence is decidable as a consequence of the strong normalization theorem. However, another notion of a standard notion of equivalence is contextual equivalence, and this notion of equivalence is in fact in general much stronger than just beta equivalence. And this was one reason why methods based to compute at least approximation of contextual equivalence are largely applied in application, especially, for example, for optimization techniques in functional programming languages. So we can get an idea of why contextual equivalence is stronger than just beta equivalent just by a very simple example. Here you can see two different normal forms of a certain polymorphic type, and they are distinct because in fact there is some polymorphic variable f which is instantiated in the first case in X, in the second case in Y, and it's applied in a different way. But however, if you now imagine some context applied to these terms, well, the context should in fact somehow instantiate or apply this variable f to some object term of type for all x, x implies x. Now you can see that a term of type for all x, x implies x is in fact can only be the identity program. But when we instantiate the variable f now with the identity program, whatever the term we take, we can see that this evaluates to the same normal form. So this suggests, it shows in fact that a context is not able to make a difference between these two terms, which are instead distinct from the viewpoint of beta equivalence. Now, we said contextual equivalence is undecidable in System F, but in fact, we can actually show it's not too difficult to realize that contextual equivalence is already undecidable in F1. And for this, it suffices to recall that the Kalmar elementary functions are representable in System F1. In fact, we have seen that all the super elementary functions are representable in F1. And in fact, it's well known from the literature that the problem of the equality problem for Kalmar elementary functions is undecidable. So from this, we already obtained some undecidability property. Can we argue in the same way in the case of FAT? We cannot, because we know that FAT is much less expressive than F1. In fact, the representable functions here are just the extended polynomial. And in fact, the problem of equality for the extended polynomial was shown some 20, 25 years ago to be decidable, in contrast to the one with Kalmar elementary functions. So here we have a divide, because we can prove that if we focus our attention just on the types for numerical functions, well, then we get the contextual equivalence is already undecidable in F1 and actually already in ML, while contextual equivalence is decidable if we take system FAT. One might imagine at this point that maybe contextual equivalence might happen to be decidable in the whole of FAT, but this is not the case. In fact, our last result here is that contextual equivalence is undecidable if we consider the whole of FAT. And for this, to prove this fact, we basically reduce the type inhabitation problem that we had seen to be undecidable at the beginning to contextual equivalence. More precisely, for any type, we construct terms, true terms, and by a proof search argument over the possible context, we see that a context that will be able to separate these two programs can exist precisely when we can find a proof of A, so a term of type A. So we reduce the fact that A is inhabited to the fact that these two terms can be separated. Okay, so this is the general picture that we described. As we said, our goal in investigating type-related properties of FAT was also to try to shed some light on what makes these properties undecidable in the case of System F. So for what concerns type inhabitation, we have seen that the undecidability, the fact that undecidability already holds for FAT suggests that this fact has little to do with predicativity, and in particular, this somehow suggests, so the argument that we have seen somehow suggests that here undecidability is really a sort of first order phenomenon, can be seen as a sort of first order phenomenon. Instead, for what concerns type checking, so our decision algorithm for FAT, really highlights the role of cyclic equations in making type checking undecidable, because we know that on the one hand, if we take ML, we know that also in this case, cyclic equations cannot be solved because we use first order unification. We take part, we have decidability just precisely, essentially, because we all terms which lead to cyclic equations cannot type check. Instead, in F1, we have cyclic equations and we have undecidability. In particular, this fact suggests that one might consider other kind of restriction without having a ranked restriction like ML, but where without the restriction when, for example, one restricts the use of polymorphic variables to be linear or affine, because in fact, the possibility of constructing a cyclic equation requires a polymorphic variable to occur at least twice. And finally, the undecidability of contextual equivalence also suggests that this problem is in some sense independent from the predicativity and predicative extension. So for those who might be interested, the paper that appeared this year at CSL, always by me and Luca, we explored a different kind of restriction of the polymorphic type discipline, which leads to define fragments which are not at all predicative, but where in some cases we can show that contextual equivalence is actually decidable. But this goes in a sort of orthogonal direction with respect to that of considering restriction of predicativity, but also with respect to the kind of restriction that you find in systems like ML, where we have seen that contextual equivalence remains undecidable. Okay, so I will stop here. So I thank you all very much for watching, and for any question or comments, well, see you at FSCD.
Paolo, thank you very much for your talk.
Welcome.
Are there any questions?
Can you hear me?
I can hear you very well.
Okay,
Can you hear me? Yes.
Yes.
Okay. Let me see if there are any questions in the chat or otherwise. Let me ask you a question about your use of type checking and typing. So in your tables, you have these two lines, and for all the systems they are the same. And in my general experience, type checking and typing are kind of equivalent problems. They are the same decidable, undecidable complexity. But you had two entries. Is there a specific reason for having that? So are there subsystems of system F where they really diverge, the complexity of typing?
No, I think you're right there. So it's, for instance, in our case, it was a standard to prove decidability of the typability problem. We used like a standard argument to reduce it, starting from the decidability of type checking. To my knowledge, I think you're right. So the two properties generally agree. So
okay. So there isn't some surprise here that I wasn't aware of. No. Okay, yeah. There's a question. Ralph Mattes is raising his hand. So Alejandro, Ralph, please. Ralph,
you can just talk. You are unmuted.
Ralph, we can't hear you. You are unmuted, so you can speak.
Okay. Good, but the video is still not allowed. Okay. Yeah, I mean, yes, this was all very nice and interesting. And I just wanted to say, yeah, avoid a confusion. So the type checking is, of course, only interesting for the query style systems. And of course, in the paper, this has always been done in the right way. But I think here in the talk, it was not so clear that, because most of the time atomic polymorphism is presented in church style. And of course, the question here was, is it decidable in query style? And yeah, but the problems were all solved properly.
Yes, it is true. So of course, in the presentation in church style, so with all type annotation, the problem becomes decidable.
Yeah, in trivial ways. Yeah, as for the full system F. Yeah.
Yep.
Yeah, but of course you solved the real problems. Yeah, and but I think in the talk it was not so clear that you switched always in the intelligent way between church and query.
Yes, you're right. So when we were talking about type checking, we were talking of a formulation of that in query style, so without explicit type annotation. Yes, for sure.
Yeah, okay, but thanks a lot. It was very stimulating.
Okay. Other questions? I have a small question still. So in your table, so type inhabitation is undecidable for F with atomic types, FAT. And you said it's undecidable for ML. Now, in my kind of vague intuition, it's a kind of a subsystem of FAT of ML. So I would think that that proof might go through, but somehow it doesn't, it seems. I mean, if the question is open in your table. So why does the undecidability of type inhabitation for FAT not immediately extend to an undecidability in ML? Or is
because ML is not a fragment of system F, of atomic system F.
No, I would think it the other way around, basically, but that's not even that's the case.
Oh, not even that, because so in ML you have a restriction over the rank. Okay, so
yeah,
you cannot have universally quantified types that occur to the left of an implication. Instead, in system FAT, you have no restriction like that. So the types are precisely the whole the types of system F. Yeah. So there is only a restriction on
yeah, and the undecidability proof. So I know it's not really a subset of it, but the undecidability proof in FAT really uses this fact that you have that you can have nested.
Yes, because it is based on an encoding of a first order system. If I remember well, the encoding uses nesting of first order quantifiers, which gives a nesting of second order quantifiers.
Okay, because that's the predicate logic implementation that you're referring to.
Yeah, it's really a first order argument actually. So.
Yeah. Okay, thank you. Yeah. Okay. So, other questions? I don't see any other questions, neither in the chat. So, Paolo, thank you again for this very nice presentation.
Thank you.
And then we